Hi guys, Mr. Kane here, and Finnegan Harris Kane also. We're going to present to you today the emission spectrum of a hydrogen atom. Alright, so the first question I was asked in my series of questions that I asked you guys to ask, important questions, was how is baby Finn? The answer to that is, as you can see, he's doing very well. He's just about 7 pounds. I think he's 6 pounds 12 ounces right now. And he seems to be spending a lot of time sleeping, eating, and crying. Except for he's not sleeping at night. I should be back on Wednesday, and I've left the sub instructions on what part of the lab I want done today. So make sure you get that done as much as you can. If you don't get it finished, try and finish it up for homework. I'm going to try and explain as much as I possibly can. How do you go from wavelength to frequency? Let us suggest, for instance, that we have a wavelength of, I don't know, somewhere around 500 nanometers that we've been given. To go from wavelength to frequency, you're going to use the equation C equals lambda nu, which lambda is wavelength and nu is frequency. C is going to be, since this is in nanometers, C is going to be 3.00 times 10 to the 17th nanometers per second as a speed. I'm going to rearrange this equation so it solves for frequency all by itself. Do that by dividing both sides by lambda, so that frequency is C over lambda. So we're going to say 3.00 times 10 to the 17th nanometers per second. We're going to divide that by the 500 nanometers. That takes care of nanometers and nanometers. And if I can get my handy dandy trusty rusty calculator out here, 3.00 times 10 to the 17th. I'm going to divide that by 500, and we're going to get 6 times 10 to the 14th. So the answer that I'm going to write down over here is going to be 6.00 times 10 to the 14th per seconds, which I prefer to call it 6 times 10 to the 14th hertz. Second question, how does an atom emit a photon? Okay, essentially here's the deal. We're talking about a hydrogen atom when we do this, so there is my nucleus with my single proton. Surrounding that nucleus are various orbitals that are basically concentric rings. It can have a whole bunch of different orbitals. I'm going to shade this nucleus red so that we can tell that it's a nucleus. This is the first orbital, so n equals 1. This is n equals 2, and this is n equals 3. So there's different concentric rings where these electrons can live. Turns out that hydrogen only has one electron, and I'm going to color that electron in a different color than the rings here. So here's the electron right there. Okay. If I'm going to be asking the question, how does an atom emit a photon, what we're going to do here is this. In order for anything to give off light or energy, it's going to have to first absorb some energy. So the first thing it has to do is it has to get some incoming energy. This could take on the form of electricity, it could take on the form of light, X-rays, gamma rays, radio waves, any kind of energy you like gets thrown into the atom. That electron is going to absorb that energy right there in the first step. So they're going to become one packet. Now here's the dealio. When you have a certain amount of energy, you can be in a certain level. Think about Indy cars, for instance. If you ever watched Indy cars go around in a circle, the slower the car moves, the closer to the inside of the track it is. So this first electron had almost no energy, but now it's gained more energy, so it's going faster. Okay? An Indy car that's going faster moves higher up and farther out on the curves. So that means that this electron is going to have to jump up. This is what's known as a quantum leap. Okay, I'm going to have a quantum leap up 2 levels. And I'm going to label that quantum leap. Sorry about that. That is a UM. All right, so here's the electron up here. And that electron can exist in that state as long as it can hold on to that energy. It's not going to be able to hold on to that energy forever, because if you've ever watched an IndyCar race and you see somebody gain too much energy, you know that they spin out and they crash. All right, so they're going to the electron is going to wind up going back to its ground state. It's eventually going to fall down. But in order to fall down, it has to get rid of that energy that it had, so it's going to have to emit that energy. Okay, so that energy that it emits is going to be the amount of energy that's necessary to go from a level 3 to a level 1, which I believe is another question that we were asked. I think it's the next question. So, real quick summary. The atom starts in the ground state, where the electron starts out in the first energy level. This is hydrogen, so it only has that one electron. That makes this a real simple model to use. All right. Now, in order for that atom to emit a photon, first the electron has to absorb some energy, so it's going to get hit with this energy that's here. It's going to jump up a level, or 2, or 3, or 4. It has to jump up at least one level, and that's called a quantum leap. It's going to move around in that orbit, and we're not going to see anything. When that electron falls at least one level, it's going to give off some energy. This energy is what we call a photon. Okay, sometimes that photon is going to be in the visible light range. If it's a higher energy wave, it's probably going to wind up being ultraviolet, or it could possibly be an X-ray or a gamma ray. If it's lower energy than visible light, then it's going to probably be a microwave or a radio wave. It might actually be infrared also. So how do you calculate the energy of a photon that is emitted when an electron falls from one level to another? For example, from the 4th level to the 1st level. Well, we've got this equation, negative 1312 kilojoules per mole divided by n squared. Notice, guys, the use of the letter n. I use the letter n to label each of the energy levels. Okay, so there was an energy level 4 and an energy level 1 that the electron moved from and to. So negative 1312 kilojoules per mole divided by 4 squared will tell me the amount of energy that the electron has when it's at that particular energy level. Negative 1312 kilojoules per mole over 1 squared is going to tell me how much energy that it has at the first energy level. Now that's an easy problem. 1 squared is 1. Negative 1312 divided by 1 is negative 1312 kilojoules per mole. Okay. So I gotta get out my handy dandy calculator here. Squared n paren equals negative 82. All right, so I get negative 82 kilojoules per mole at the 4th energy level. So what that looks like is this. Here's the nucleus, 1st energy level, 2nd, 3rd, and finally the 4th energy level. So up here in the 4th energy level, negative 82 kilojoules per mole. Down here at the 1st energy level, negative 1312 kilojoules per mole. When the electron moves from one to the next, you notice that it's a difference in energy. So what we want to do is we want to take negative 1312 kilojoules per mole, and we want to subtract the negative 82. Now I get an answer that makes sense. It's an answer that's somewhere in between, so negative 1230. So negative 1230 kilojoules per mole is how I answer this question here. How do you calculate the energy of the photon that is emitted? Okay. Negative 1230 kilojoules per mole was the amount of energy on that last problem. How do you go from energy to wavelength or frequency? Well, let's take a quick look. Okay, so here's how we're going to go from energy to wavelength. We're going to use Planck's constant equation. Energy is going to be equal to Planck's constant times the frequency. Now, I've got an energy in kilojoules per mole, which means I want to use the Planck's constant that is in kilojoule seconds per mole. All right, I'm going to rearrange this equation to solve for the frequency by dividing both sides by h. So energy over h is going to be equal to that frequency we're looking for. Again, the energy that we solved for in that last problem was negative 1230 kilojoules per mole. H is 3.989 times 10 to the negative 13th kilojoule seconds per mole. The kilojoules and the kilojoules cancel, the mole and the mole. The per second that we're wind up with is what we're left over with, which is going to give us our frequency. 3.08 times 10 to the 15th, and that's in hertz. Now, technically the calculator says it's a negative amount of frequency, but that's not possible. The negative is talking about the energy and that it's an energy loss. So we're just going to consider that 3.08 times 10 to the 15th is the frequency of that photon that was lost. How do I get from wavelength from there? Well, I'm going to use the equation C equals lambda nu to get there. And I'm going to be solving for wavelength. I have the frequency and I have the speed of light. I'm not going to show you how to do that because I've shown you that already. All right, and pretty much that's all the questions that I got, folks. All right, I think I could take a quick look at the lab here and show you guys that you've solved this first set of equations here. For instance, you've got this one, you've got negative 1312. And for the second one, you wound up finding out that negative 1312 divided by 2 squared is negative 328. So when you get to this graph here, negative 1312 is already graphed for you. The next thing that you have to graph, and you'll be doing this with a ruler, which are in the center of my lab table. We take a pen, and I'm going to find where negative 328 is. Negative 328 is somewhere between negative 300 and negative 400. And you're going to wind up drawing a line across here. Okay, now notice, guys, this is n equals 2. This is n equals 1. Okay, you'll do this for n equals 3, 4, 5. Let's see, how many did the lab? And 6. Okay, so you're going to do that for all 6. There is an n equals infinity here because technically the electron has the ability to leave the atom. Okay. Part 3 here says draw a series of arrows to represent the electrons falling from the 6th energy level to the 1st, to the 5th, to etc. Okay, so these electrons are going to have to be able to fall from an energy level to another energy level. So let's just say, for instance, I'm just going to draw these in here. This is not right. And I don't think I have a 3, so I'm going to draw in a 3. I might have too many. All right, so basically what you're going to be doing is you're going to be drawing in the fact that an electron can fall from 6 to 1. You'll be drawing in the fact that an electron can draw from 5 to 1, from 4 to 1, and so on and so forth. And you're going to do it a lot better than I am because A, not only is your computer not going to mess up because you're doing this with paper and pencil, but you're going to be doing this with a set of lines. I've got a key made up for you guys so you understand what it's supposed to look like. Try doing the calculations, try doing it without copying directly from the key, okay? You'll answer these questions from that chart that you create, and then hopefully you've already done this. This is basically the mathematical end of that graph, okay, of that chart that you created. I want you to show the work for just this one, for an energy level drop from 6 to 1. And then after that, you can just do the calculations and throw them on here. Now, if you've done the worksheets previously, you actually have some of this stuff done. If you're savvy, you can find it and copy it rather than redoing it. Some of it you'll have to retype. Recalculate. The type of E&M, I'm just looking for the color or whether it's microwave, radio wave, infrared, etc. Okay. The place that you're going to find out that information is that colorful sheet that I gave you guys at the beginning of the unit. All right.